Have you ever been in that situation, maybe on vacation, maybe just stepping out your front door where the air just hits you? That thick, warm, humid blanket that makes your clothes stick to your skin, making every movement feel like, well, a struggle? For me, it immediately brings to mind stepping off the plane in places like Cebu, and it truly makes you appreciate the science we're about to unpack. Today, we're not just talking about flipping a switch and feeling a blast of cold air. Oh no. We are going on a deep dive into the science, the sophisticated systems, and the smart design behind creating true indoor comfort, particularly in those challenging, relentlessly hot, humid climates. Our mission today is to unpack the fundamental principles of air conditioning, how designers approach it in specific climatic conditions, and the different systems that make our indoor spaces not just tolerable, but genuinely comfortable. We're drawing primarily from Module 2 Air Conditioning, a truly fascinating document that uses Cebu City in the Philippines as its primary example. It offers a fantastic real-world case study for understanding these complex interactions. Okay, let's unpack this. What is true comfort, and how do we achieve it when nature throws its warmest, most humid challenges at us day in and day out?
It's a critical question, absolutely. Especially when you look at regions like the Philippines, where air conditioning truly shifts from being, a luxury to an absolute necessity. The source material frames it perfectly by focusing on Cebu City and province. This area is a prime example of a tropical country with what's officially classified as a hot humid climate, specifically a type 3 climate. What that means, crucially, is there isn't a pronounced, distinct dry season. It's consistently warm and, well, perpetually wet year-round.
And when you're in a climate like that, the core problem becomes immediately apparent, doesn't it? How do the prevailing conditions of Cebu stack up against what humans actually perceive as comfortable? Our bodies, for all their adaptability, have a pretty narrow comfort zone, especially when it comes to temperature and humidity.
Absolutely. Let's dig into Cebu's temperature profile first. The data from our source shows that May is consistently the warmest month. We're talking an average temperature hitting a sweltering 32.9 degrees Celsius. Now compare that to the coldest months, January and February, which average around 23.8 degrees Celsius.
Wow, even that coldest average is pushing the upper bounds of comfort for most people, isn't it?
Exactly. Digging a bit deeper into the annual cycles, the warm season in Cebu actually stretches from about April 10th to June 16th. During this time, daily high temperatures regularly soar above 32 degrees C. The absolute hottest day on record in this period is typically around May 28th, where you're looking at an average high of 33 degrees C and a low that only dips to 26 degrees C.
A 26-degree low. That's remarkably warm for what should be the coolest part of the day.
It is. Conversely, the cold season, such as it is in a hot, humid climate, runs from roughly December 15th to February 15th. During this time, daily highs generally stay below 30 degrees C, and the coldest single day is typically February 5th, with an average low of 24 degrees C and a high of 30 degrees C.
So even in their cold season, it's still consistently warm.
That's right. If we look at the overall annual temperature data for Cebu, the average minimum temperature is about 24.08 degrees C. The average normal temperature is 27.39 degrees C, and the average maximum temperature reaches 30.99 degrees C. What's fascinating here and really underlines the challenge is how these figures compare to the human comfortability limit for temperature, which is a surprisingly narrow range of 22 degrees to 26 degrees C.
So the stunning takeaway there isn't just that it's hot, it's that Cebu's coldest days are still right at the very upper edge of what humans find comfortable, maybe even slightly above it. This fundamental mismatch right from the start highlights why simple fans often aren't enough. You're constantly fighting an uphill battle against nature itself. Quite humbling, isn't it? For all our advanced technology, our bodies are still incredibly sensitive, operating within such a tiny comfort window. It really underscores why simply toughing it out often isn't a viable option for long-term well-being and, productivity.
Absolutely. And that's just temperature. The other major player in tropical climates, the one that makes the heat feel so much more oppressive, is humidity.
Ah, yes, the humidity, the stickiness factor.
Precisely. Relative humidity, or RH, is essentially the actual amount of moisture vapor in the air, compared to the maximum amount of moisture the air can hold at that specific temperature. When the air can't hold any more moisture, it's at its saturation point, and that's when you see condensation, like dew forming on surfaces. Our source emphasizes that the RH for Cebu tends not to vary much throughout the entire year.
Really? It's just consistently high?
Pretty much, which is quite remarkable given the consistent warmth. However, there are still some detectable extremes. The highest relative humidity is typically observed from October to December, reaching a value of about 81%. On the flip side, the lowest RH is found in April at around 75%.
Okay, so April is about 7% drier than those later months. But let's be clear, 75% is still incredibly high, right?
Abundantly clear.
Yeah.
This raises an important question. How do these figures compare to the human comfortability limit for relative humidity? That ideal range is between 40% RH and 60% RH.
Wow.
Yeah. You can immediately see the even greater discrepancy here than with temperature alone. We're talking about conditions that are consistently 15 to 40 percentage points above the comfortable range.
40 points.
This is why even a moderate temperature in Cebu can feel stifling. Your body cools itself primarily through the evaporation of sweat. When the air is already saturated with moisture at 75–80% RH, your sweat simply doesn't evaporate effectively.
It just sits there.
Exactly, leaving you feeling clammy, sticky, and far hotter than the thermometer might suggest. I remember once in a hotel in Southeast Asia, the AC was blasting cold air, but I still felt clammy. It wasn't until I realized it was likely just recirculating the humid air without properly dehumidifying it that I truly understood why dehumidification is like half the battle.
That's a stark difference. So it's not just that it's hot, it's that it's sticky hot pretty much all the time, making our natural cooling mechanisms almost useless. Let's actually walk through Table 1 from our source material, temperature and relative humidity range for Cebu City, month by month. It really puts things into perspective. For example, in January, the minimum temperature is 23 degrees C, which is just barely within that 22–26 degrees C comfort zone. But the average hits 26.3 degrees C, already pushing it. And the humidity, a minimum of nearly 80% RH, averaging 87.2%. You're starting the year already way out of the comfort zone on humidity.
Precisely. And if we look at February, it's quite similar. Averages in the mid-26s for temperature and humidity averaging around 85.6%. March starts to see the temperature creep up a bit, with the average hitting 27.2 degrees C. And while the humidity drops slightly to an average of 82.6%, it's still incredibly high.
So that slight drop isn't enough to bring us into comfort.
Not at all. Then we hit April, where the minimum humidity drops to 73.4%, the lowest of the year.
Okay, some relief.
Well, yes and no, because the average temperature is now 28.2 degrees C, and the maximum hits nearly 32 degrees C. So even though it's technically drier, it's getting significantly hotter, making any relief feel pretty minimal.
Right, and that trend continues into May, which you said is the warmest month.
That's right. The average temperature is 28.4 degrees C, maximum is 32.1 degrees C, while the average humidity is back up slightly to 82.8%. Here's where it gets really interesting, physiologically speaking. The combined effect of high temperature and high humidity is what truly impacts human perception of comfort. Think about it. 30 degrees C at 80% RH feels vastly uncomfortably hotter and more oppressive than 30 degrees C at 40% RH. As we mentioned, when the air is already saturated with moisture, your body's primary cooling mechanism, sweating and evaporation, becomes far less effective.
So your internal thermostat is working overtime but getting nowhere.
Essentially, yes. Your sweat just sits on your skin instead of evaporating and cooling you down, which is why you feel so clammy and sticky.
So even if the temperature dips slightly, if the humidity stays stubbornly high, it still feels incredibly uncomfortable. It's not just about cooling the air, it's crucially about dehumidifying it too. That's a key takeaway right there, and it's why a simple fan, while offering some air movement, can often feel like it's just blowing hot, sticky air around in these climates. It's not removing the moisture.
Absolutely. The perception of comfort is a complex interplay of multiple factors, and humidity plays an outsized, often underestimated role in hot climates.
Okay, so we've established the climate challenge is significant, relentless even. Given these hurdles, how do architects and designers even begin to create comfortable indoor environments without just resorting to blasting cold air constantly? This is where bioclimatic analysis comes in, right? Designing with nature before fighting against it.
Exactly. That's the ideal starting point.
Yeah.
Let's define these core bioclimatic concepts first. Bioclimatic, at its heart, is the study of how climatic conditions specifically affect living organisms, particularly humans, in terms of their physiological comfort and well-being. Building on that, bioclimatic analysis is a systematic procedure for assessing thermal comfort directly in relation to the external climate. Its entire purpose is to identify what our source calls desirable adaptations of the structure.
Meaning changes to the building itself?
Yes. How the building itself should be designed, oriented, shaped, and constructed to meet human comfort needs under those specific climatological conditions. It's about designing buildings that are inherently more responsive and comfortable, minimizing the need for active, energy-intensive cooling later on.
So it's almost like a diagnostic tool for designers, showing them where the natural climate falls short and how the building itself can strategically bridge that gap before mechanical systems even enter the equation.
Exactly. And our source mentions two primary methods for this assessment. The Givoni method, developed by Professor Baruch Givoni, and the Olgier method, by architect Victor Olgier. For this deep dive, our source specifically focuses on the Givoni method, which is a widely recognized approach. The core idea behind both these methods is to plot climatological data, specifically temperature and humidity, onto what's called a psychrometric chart.
A psychrometric chart sounds complex. What does it actually show?
Think of it as a climate roadmap for designers. It's the graphical representation where every single point on the chart represents a specific combination of air temperature and moisture content, or humidity. And importantly, marked right on this chart, there's a specific zone, sometimes called the comfort zone or comfort island, the range of temperature and humidity where most humans feel thermally comfortable. Designers plot the actual climate data, like Cebu's monthly averages, onto this chart.
Ah, so they can visually see how far off the local climate is from that comfort zone.
Precisely. It instantly shows them how far off the local climate is from that comfort island, and crucially, which direction they need to move. Do we need to cool, dehumidify, heat, humidify, or some combination to bring the indoor environment into that sweet spot? It becomes a visual guide for strategic design decisions.
And to do this effectively, you need very specific granular data, right? It's not just a general sense of it's hot and humid.
Correct. For a proper bioclimatic analysis, the minimum climatic data required includes, first, outdoor air temperatures, specifically the monthly maximum average and monthly minimum average values. Second, you need the relative humidity, again, the monthly maximum average and monthly minimum average values.
The same data we looked at in Table 1.
Exactly. If we connect this to the bigger picture, this isn't just a collection of numbers for a report. This data forms the absolute foundation for informed design decisions. It guides how a building should interact with its environment. This analysis helps a designer understand whether they can achieve comfort passively, maybe through natural ventilation or shading, or if active mechanical systems like air conditioning are indispensable, and, to what extent. It's about optimizing the building's envelope and orientation first before layering on energy-intensive solutions.
Can you give an example? Like for Cebu, what might that analysis suggest?
Sure. So for a place like Cebu, where the psychrometric chart would show constant high humidity and likely intense radiant heat from the sun, a designer might prioritize very specific passive strategies based on that analysis. This could include designing deep roof overhangs and carefully oriented window placements to block direct sun exposure throughout the day, minimizing solar heat gain. They might emphasize maximizing natural cross-ventilation with strategically placed openings, windows, louvers to allow breezes to flow through. Even if those breezes aren't fully cooling, they help with moisture removal and perceived comfort. They might also specify building materials with high thermal mass or low thermal mass, depending on the strategy, maybe materials that absorb less heat, or materials that quickly shed heat overnight to prevent the building fabric itself from radiating heat indoors long after the sun goes down.
So it's about letting the building itself do as much of the cooling work as possible before you even think about turning on the AC.
Exactly. This analysis becomes the blueprint for a truly responsive, climate-appropriate building.
Building on that context and acknowledging that passive design can only take us so far in such extreme conditions, let's turn our attention to the technological solution that fills the gap. What is air conditioning, according to the official definitions? Because for many of us, it's just that magic box that makes the room cold, but clearly it's far more nuanced than that.
It absolutely is. And our source provides an excellent comprehensive definition straight from Article 8.1 of the Philippine Society of Mechanical Engineers, or PSME, Code. It defines air conditioning as the process of treating air so as to simultaneously control its, four key properties.
Okay, 4 things. What are they?
1, temperature. That's the obvious one, regulating the hotness or coolness. 2, humidity. As we've discussed, managing the amount of moisture in the air, absolutely critical in hot, humid climates. 3, cleanliness. This is often overlooked but incredibly important for indoor air quality. It involves filtering out dust, pollen, mold, spores, other particulates.
Right, the filters you're supposed to clean or change.
Exactly. That's crucial for respiratory health and overall comfort. And 4, distribution. Ensuring that the conditioned air actually reaches the entire space effectively and evenly. All of this is done to meet the specific requirements of the conditioned space, creating an environment optimized for human comfort and well-being.
So it's not just about a blast of cold air, it's truly a holistic air treatment system managing multiple variables all at once.
Exactly. The emphasis in the definition on simultaneously control is key here. It highlights that a true air conditioning system doesn't just lower the temperature, it actively manages all these parameters together. This explains why, in high humidity, just opening a window often feels worse, even if the outdoor temperature drops slightly.
Because you're bringing in more humid air.
Right, you're bringing in more humid air, which makes you feel stickier and less comfortable because that crucial dehumidification step isn't happening. And there's a crucial nuance for the Philippines, as specified in our source. Air conditioning there is focused only on comfort cooling. Heating is simply not required due to the prevailing hot, humid climate.
Makes sense.
So, while AC systems in colder climates might also provide heating, in the Philippines, their primary, almost exclusive function is cooling and dehumidifying to achieve that desired comfort zone. What's fascinating here is how the definition itself adapts to the specific needs of the region. It's a precise, targeted process tailored for the unique challenges of the local climate. This impacts everything from system design to energy use.
Okay, now that we understand the core definition of air conditioning and its multifaceted nature, temperature, humidity, cleanliness, distribution, let's look at the different ways this air treatment actually happens in our spaces. We'll start with what's probably the most common and familiar type for many people, especially in smaller residential settings: the window unit.
That's the one. Our source outlines three main categories of AC systems commonly used: the unitary aircon system, the split-type aircon system, which has variations like single and multi-split, and the centralized aircon system, with subtypes like direct expansion and chilled water. For this deep dive, we'll be focusing on the unitary and split-type systems, as our source provides detailed info on them, including those practical sizing computations, which are incredibly useful if you're trying to understand capacity.
Got it. So
Yeah.
unitary first, the window box.
Right. The unitary air conditioning system is what most people recognize as a window-type air conditioner, or sometimes a through-the-wall air conditioner. It's essentially a self-contained air conditioning unit within a single cabinet. All the necessary components, the compressor, condenser coil, the evaporator coil, the fan motor, they're all integrated into one compact box. This makes them quite distinct from other systems, as the entire refrigeration cycle happens within that single enclosure.
So everything is literally in one unit, making it a fairly straightforward setup. What are the practical upsides and downsides of having everything bundled together like that? And how do designers account for its presence?
The advantages are quite clear. Firstly, user control. Because each unit is self-contained, every room essentially becomes an individual zone with independent temperature control. You can turn one off, turn another up, without affecting the rest of the space, which is potentially great for energy saving in rooms you don't use often.
Okay, individual control. What else?
Secondly, they're relatively easy to maintain or service. If there's an issue, the entire unit can often be removed for servicing or simply replaced with another unit, which can simplify repairs compared to more complex systems. And thirdly, they're space-saving in terms of the indoor components, as they fit compactly within a window or a dedicated wall opening. They don't need additional indoor plumbing for refrigerant lines or ductwork, just a simple drain for condensation.
Okay, those are definite pluses. But what about the drawbacks?
Well, there's some distinct disadvantages. Our source notes that they generally have a shorter lifespan compared to some other systems. This might be due to the components being exposed to the elements on the outside, or maybe just the constant vibration within that single enclosure. But perhaps the most significant disadvantage, especially from an aesthetic and architectural viewpoint, is what our source calls the issue of protruding units to exterior present challenges or problems in architect's design.
Ah, the look of them.
Exactly. These units often stick out from the building facade, which can be an eyesore, disrupt the building's clean lines, or even complicate the structural integrity of the wall if they're not properly supported and sealed. Plus, if they're placed in a window, they obviously block a significant portion of natural light in the view.
That makes sense. You often see them as an obvious addition, sticking out, sometimes looking like an afterthought. But if you are installing one, what are the best practices for placement to ensure it actually works efficiently? The source gives some practical tips that go beyond just finding an empty space in the wall.
Absolutely. The source provides 3 key guidelines for locating a window-type ACU to ensure excellent performance and, importantly, energy efficiency. First, there should be no obstructions surrounding the air conditioning unit. You need unimpeded airflow both into the front grille for cooling and out of the back sides for heat rejection.
So don't block it with curtains or furniture.
Right. Any blockage dramatically reduces its efficiency and can even lead to the unit overheating. Second, the bottom portion of the unit should ideally be installed between 0.75 meters and 1.50 meters above the finished floor level.
That specific height range. Why?
It's crucial for achieving excellent circulation of conditioned air throughout the room. Cold air is denser and naturally sinks. If it's installed too high, the cold air might just fall straight down, leaving the upper parts of the room warm. If it's too low, it might not mix well with the warmer air higher up, creating cold spots near the floor. That height range, roughly 2.5 to 5 feet, promotes optimal mixing of the cool air with the room air.
Okay, height matters for circulation. What's the third tip?
Third, you should try to avoid installation where the sunlight hits the outside unit directly. If it's unavoidable, the recommendation is to build an awning to shade the unit.
Why is direct sun such a problem?
Direct sunlight on the outdoor component, the condenser coil at the back, significantly increases the heat load on that coil. It forces the unit to work much harder to reject the heat it has removed from the room, plus the heat from the sun. This dramatically reduces its efficiency and increases energy consumption. It's almost like trying to cool a refrigerator while leaving its door open in direct sunlight.
Got it. Shading helps keep the outdoor part cooler, letting it do its job better.
Precisely. It allows the condenser to dissipate heat more effectively, saving energy.
Those are really helpful practical tips that immediately make sense from a physics perspective. Okay, now let's talk about sizing. How do we actually figure out what size of unitary air conditioning unit we need for a given space? The source provides some really useful shorthand computations that designers use for preliminary estimates, right?
Yes, these are fantastic for quick preliminary calculations. They help designers get a ballpark figure before diving into more complex, detailed load calculations, which consider things like window area, insulation, occupancy, lighting loads, etc. The source gives us two simple rules of thumb for unitary air conditioning cooling load computations. Rule A states that 1 HP, or horsepower, which is a common way these units are rated, is roughly equivalent to cooling an area of 15 square meters. Rule B states that 1 square meter requires approximately 500 B2, or British thermal units per hour.
B2, that's a direct measure of cooling power.
Yes, it's a measure of heat removal. A BTU is essentially the amount of energy required to raise the temperature of 1 pound of water by 1 degree Fahrenheit. So B2 per hour tells you how much heat the unit can remove from the space each hour. You can use either the HP rule or the B2 rule to get a quick estimate of your cooling needs.
And the source includes a table with actual unit capacities.
Yes, Table 2, Capacity of Unitary Aircon, based on a Koppel window type ERA series catalog. This table lists various model numbers and their corresponding cooling capacities in HP, B2, and also kJA, kilojoules per hour. It also includes their input power in watts and their ER.
ER, energy efficiency ratio.
Correct. ER is a crucial metric. It indicates how many BTUs per hour of cooling are delivered for each watt of electrical power consumed.
So for us, the listeners, ER is essentially the miles per gallon of an AC unit. Higher is better.
Exactly. The higher the ER number, the more cooling power you get for every unit of electricity consumed. It's not just a technical spec, it's a direct indicator of how much money you'll likely save on your monthly electricity bill. That makes it a critical factor, especially in a hot climate where the AC might run for many hours a day.
Can you give an example from the table?
Sure. The table shows a KWR AC6 M5A model. It's rated at 0.6 HP, provides 5,400 B2 of cooling, and has an ER of 9.77. Compare that to a much larger KWR18 M5A model. That one is 2.0 HP, provides 18,000 B2. Actually, the table says 18,990 B2. Let's use that. And its EER is 9.50.
Interesting. So the larger one is slightly less efficient per watt in this case?
In this specific comparison, yes, slightly. But generally, you want the highest EER you can find for the capacity you need. Even small differences in ER can add up significantly on your electricity bill over the lifespan of the unit.
Okay, here's where it gets really interesting. Let's put these numbers to work. The source gives a sample project, a small office that measures 5.00 meters by 6.0 meters. How do we determine the aircon requirement for this space using these shorthand calculations, and what are the practical implications of the different options?
Great question. Let's walk through step 1. Solving for the cooling capacity needed for this room. We can use either the HP or the B2 method, and they should give us a reasonably consistent result for a preliminary estimate.
Okay, let's try the HP method first.
Right. Solution 1, using HP cooling capacity. First, we calculate the area of the office. 5.0 meters multiplied by 6.0 meters equals 30 square meters.
Okay, 30 square meters.
Then we apply the rule of thumb. Aircon requirement divided by 15 SQM per HP. So 30 SQM divided by 15 SQM per HP equals 2.0 HP.
Simple enough. We need 2 horsepower of cooling.
Correct. Now, referring back to Table 2, our recommendations based on available models would be Option A. Use 2 units of the KWR09M5A model. Each of those is rated at 1.0 HP, so 2 of them give us a total of 2.0 HP. Option B. Use 1 single unit of the KWR18M5A model, which is rated at 2.0 HP. Both options effectively meet the calculated 2.0 HP requirement based on this rule of thumb.
Okay, now let's try the other rule using B2.
All right. Solution 2. Using B2 cooling capacity. Again, the area is 30 SQM, applying this rule. Aircon requirement, I believe, is multiplied by 500 BTU per SQM. So 30 SQM times 500 BTU per SQM equals 15,000 BTU.
So we need 15,000 BTU per hour of cooling capacity.
That's the target based on this rule. Now let's look at Table 2 again to see how the models match up. If we consider using 2 units of the KWR09M5A, the table says each provides 9,573 BTU. So 2 units together would give us 19,146 BTU total.
That's quite a bit more than the 15,000 we calculated.
It is. It suggests this option would be somewhat oversized based on the 500 B2 rule, but it would certainly provide strong cooling. Now, if we look at using 1 unit of the KWR18M5A, the 2.0 HP model, the table lists its capacity as 18,990 B2.
Also significantly above the 15,000 B2 target.
Yes, both options recommended based on the HP calculation provide substantially more B2 than the simple B2 calculation suggests is needed.
So that's interesting. The shorthand rules give you a ballpark, but the actual available units might force you to slightly oversize.
That often happens. The rules are estimates. Factors like sun exposure, number of occupants, equipment heat load aren't in these simple rules, but affect real-world needs. So slight oversizing, especially using catalog units, is common and often provides a safety margin. So we're looking at needing roughly 2.0 HP or 15,000 B2, but the practical options are closer to 19,000 B2, whether using 1 large unit or 2 smaller ones.
As a designer, or even just an office manager making this choice for a 30 square meter space, what are the real-world considerations that guide that choice between 1 2.0 HP unit versus 2 1.0 HP units?
That's where the art meets the science, isn't it? For a 30 SQM office, choosing between a single 2.0 HP unit and 2 1.0 HP units involves several important trade-offs. Firstly, think about zone comfort and redundancy. 2 smaller units offer superior zone control.
Meaning you can cool different parts of the office independently.
Exactly.
Yeah.
In an office, you might have individual workstations or areas that need different levels of cooling, or perhaps only half the office is occupied at certain times. 2 units allow you to turn off one or run them at different settings, which can save energy. Furthermore, and this is crucial for a business, they provide redundancy. If one unit fails, you still have some cooling capacity from the other.
Right, keeps the office functional.
Critical in a busy office where comfort impacts productivity. A single unit means if it breaks down, you have no cooling at all. All your cooling eggs are in one basket, so to speak.
Okay, zoning and redundancy favor 2 units. What else?
Secondly, air distribution. 2 units placed strategically can often achieve more even air distribution across a rectangular space like this office. They can prevent hot or cold spots that might occur with a single unit trying to push air across the whole 6-meter length. Thirdly, noise. While window units are generally noisier than split systems because the compressor is right there, 2 smaller units might distribute the noise more evenly or allow for strategic placement away from noise-sensitive areas. Though admittedly, 2 compressors running might be louder overall than one larger one.
That's a maybe.
It depends on the specific units. Fourthly, energy efficiency, especially under partial load. Modern units, particularly those with inverter technology, though less common in basic window types, can modulate their output. 2 smaller units might be more efficient during times when you only need partial cooling compared to 1 large unit cycling on and off frequently if it's oversized for average use. And fifthly, installation and aesthetics. Installing 2 units means 2 holes in the wall or window, potentially more complex wiring, and a more visible presence on the building exterior. A single unit is simpler in that regard, 1 hole, simpler wiring.
So it's a balance. While both options provide the necessary cooling capacity, the choice depends heavily on the specific office layout, how it's used, the budget for installation versus long-term running costs, and how important things like redundancy and precise temperature control are.
Exactly. There's no single right answer. It requires understanding the specific needs of the space. And remember, step 2 in the sample project, which is often done concurrently with sizing, involves specifying the precise location of the ACUS and providing necessary dimensions, including that crucial installation height. This reinforces the practical guidelines we discussed earlier, ensuring proper air circulation by placing it 0.75 meters to 1.50 meter above the floor, avoiding obstructions and shading it from direct sunlight.
Right, because even a perfectly sized unit won't work well if it's installed poorly.
Precisely. These installation details are just as important as the sizing calculations to ensure efficient long-term operation and a truly comfortable indoor environment.
Okay, so that covers the familiar window unit, its pros, cons, sizing, and installation tips. But as you mentioned, they have limitations, especially for aesthetics, noise, and cooling larger spaces. So now we move to a more flexible and often more powerful and quiet option that you see a lot in both homes and commercial settings: the split-type system.
That's right, the split-type air conditioning system. As the name suggests, its defining characteristic is that it consists of two separate, distinct components connected by refrigerant piping and electrical wiring. First, you have the aircon condensing unit, or ACU, sometimes also called the ACCU. This unit contains the compressor, the heart of the system, and the condenser coil. This whole part is specifically placed outdoors.
Why outdoors?
Its primary job is to reject the heat that's been absorbed from the indoor space, plus the heat generated by the compressor itself. Placing it outside gets rid of that heat and also keeps the noisiest component, the compressor, out of the living or working space. Second, you have the fan coil unit, or FCU. This contains the evaporator coil where the cooling happens and the fan that blows air across it. This part is found indoors and is responsible for the actual cooling and handling of the air distributed into the room.
The physical separation of these two units must offer some pretty significant benefits, beyond just the obvious reduction in indoor noise from having the compressor outside. What other design freedoms or functional advantages does this split configuration unlock that a single window unit simply can't achieve? And are there any unexpected trade-offs that come with this separation?
That's a great question, and the separation really is a game changer for design and comfort. The noise reduction is huge, as you noted. That alone is a major comfort factor, especially in bedrooms, libraries, or quiet offices, where a humming window unit can be really disruptive. Looking at the other advantages, or pros, listed in our source, firstly, the split-type aircon's separate indoor and outdoor components allow for much greater placement flexibility.
Meaning the indoor part doesn't have to be on an exterior wall?
Exactly. You're not tied to a window opening or an exterior wall for the indoor unit. The SCU can be placed high on an interior wall, recessed into the ceiling, suspended from it, or even placed on the floor. This gives architects and interior designers far more freedom with building aesthetics and interior layouts. You don't have to sacrifice natural light or views just to get cooling. Secondly, these units are often more energy efficient, especially the more modern inverter-driven models, which we'll touch on. The source specifically notes that the long-term running costs of a split system are generally lower than traditional window types. This is partly due to technological advancements, higher potential EER ratings, and the ability to more precisely control the cooling output to match the actual load.
Okay. Quieter, more flexible placement, potentially more efficient. Sounds great. What are the downsides, the cons?
There are definitely trade-offs. The main one is usually the higher initial cost. A split-type system is typically more expensive up front to purchase and install compared to a window-type air conditioner of similar capacity. This initial investment can be a barrier for some. Additionally, installation and maintenance can be more complex. Because you have two separated components connected by refrigerant lines, installation requires careful running and connecting of those lines, properly insulating them, vacuuming the system to remove air and moisture, and accurately charging it with refrigerant. It's not a simple plug-and-play like a window unit.
So installation is more involved and probably needs a professional.
Almost always requires a qualified technician. And maintenance or repairs can also be more difficult or costly. For the same reasons, accessing separated components, dealing with refrigerant lines, potentially needing more specialized tools and expertise compared to just swapping out a window unit.
That makes sense. Now, within the split type category, you mentioned different styles of indoor units, the FCUs. These impact not just how they look, but also how they distribute air and fit into different spaces, right?
Absolutely. Our source details 4 common types of split-type indoor units, or FCUs, each designed to suit different architectural aesthetics, air distribution needs, and spatial requirements. It gives designers a really wide palette of options. First, we have the wall-mounted type. This is probably the most common one you'd see in residential settings or smaller offices. It's mounted high on a wall, typically near the ceiling. They're relatively easy to install compared to other FCU types and are fairly visually discreet.
Okay, the standard high wall unit.
Second, there's the ceiling cassette. These units are designed to be recessed into the ceiling, usually fitting into a standard ceiling tile grid. You often see them in commercial spaces like offices, restaurants, or retail stores.
Why are they popular there?
Because they're almost invisible, blending seamlessly into the ceiling. Plus, they typically distribute air in multiple directions, often 2 or 4 ways, providing excellent, even coverage across larger open areas without creating strong, noticeable drafts. Third, we have ceiling suspended units. As the name implies, these hang below the ceiling structure, often visible. They're used when there isn't enough space above the ceiling for a cassette, or when a more powerful, longer airthrow is needed for larger, open-plan spaces like warehouses, workshops, or gyms, where aesthetics might be less critical than powerful, uniform air delivery.
So function over form sometimes.
Pretty much. And fourth, there are floor-mounted units. These sit on the floor, often against the wall, looking a bit like a modern radiator. They are particularly useful in spaces with limited wall or ceiling installation options, maybe rooms with slope ceilings or lots of windows, or in rooms with very high ceilings, where introducing the cool air at a lower level helps with effective mixing.
It's quite a range of options.
It is. And what's fascinating here is how these different FCU types cater to such varied architectural aesthetics and spatial requirements. A designer can choose a unit that blends seamlessly or even disappears into the interior design, rather than being a prominent, sometimes disruptive element like a window unit often is. This flexibility is a significant draw for split-type systems in modern construction and renovations.
Okay, so we've seen how to do a quick sizing for a window unit using square meters per horsepower, or BFUS. How do we approach sizing for a split-type system, especially for larger or commercial spaces? The shorthand computations mentioned in the source seem to take a different approach, using tons of refrigeration.
They do. For split-type systems, especially in a preliminary design phase for larger applications like offices, retail, or other commercial buildings, the cooling load is often estimated based on the type of building or space. This is commonly expressed in square meter per ton of refrigeration, written as SCOMTR.
A ton of refrigeration, or TR, what exactly is that?
It's a standard unit of cooling capacity, particularly common in North America and in commercial HVAC contexts. It's defined as the rate of heat transfer required to produce 1 short ton, which is 2,000 pounds of ice, at 0 degrees C from water at 0 degrees C in 24 hours. In more practical terms we use today, 1 TR is equivalent to removing 12,000 BTUs per hour.
Ah, okay, so 1 TR equals 12,000 BT. That helps connect it back.
Exactly. And just for another comparison, 1 TR is also roughly equivalent to 4.71 HP, although the HP rating on split systems isn't used as consistently as TR or B2 for sizing. So when we talk about needing, say, a 5.5 TR system, you can think of the cooling power equivalent to melting 5.5 tons of ice every single day. It gives you a sense of the scale for larger systems.
Wow, so how do you use this SKDA-TR metric?
Our source provides Table 3, titled Recommended Range of Cooling Load, which is an invaluable tool for this preliminary design stage. It lists various building types and gives a typical range of square meters that 1 ton of refrigeration can effectively cool for that type of space. For example, an apartment typically requires cooling for 40 to 55 SKM per TR.
Meaning 1 ton cools a relatively large apartment area.
Right, because the heat loads are generally lower. In contrast, a bank needs cooling for only 20 to 25 SQA per TR, indicating a higher cooling demand per square meter. Classrooms are listed as 23 to 32 SQA per meter. And interestingly, a computer room or data center needs significantly more cooling, typically only 8 to 15 SQA per TR.
That's a huge difference. Why would a computer room need so much more cooling per square meter compared to, say, an apartment or even a bank? What's driving that massive increase in cooling demand?
That's an excellent observation, and it highlights the critical importance of the internal heat load when sizing AC systems, especially commercial ones. Apartments' main heat loads come from people intermittently, lights, maybe some kitchen appliances, and solar gain through windows, relatively low density overall. A computer room, on the other hand, is packed wall-to-wall with high-density electronic equipment servers, network switches, storage arrays, all of which generate a substantial amount of heat, what we call sensible heat, continuously, 24/7.
Right, those machines are always running, always hot.
Exactly. Unlike people who come and go, these machines are constantly running and radiating heat. So the cooling system has to work much harder, dedicating much more capacity per square meter just to counteract that massive internal heat generation and keep the equipment within safe operating temperatures. Similarly, a busy office building might be listed at 15 to 25 SQA TR in the table, closer to a bank than an apartment due to higher occupancy density, more lighting, and a greater concentration of office equipment like computers, monitors, and printers, all contributing to the heat load.
So the building use is a primary driver for these TR estimates.
Absolutely. Following that concept, we have Table 4 in the source, capacity of split-type aircon, again based on a couple catalog, specifically their Super Inverter 3 series. This table lists various split-type model numbers, their cooling capacity in TR and BDU, their energy efficiency ratio, and their power input in watts.
And it mentions Super Inverter 3 series. What does inverter mean in this context? You mentioned it earlier.
Right. While our source doesn't explicitly define inverter technology here, it's a very important feature in modern AC systems, especially split types. Traditional non-inverter ACs have compressors that operate at a fixed speed. They're either fully on-in, running at 100% capacity, or fully O-off-F. They cycle on and off to maintain the desired temperature. An inverter-driven compressor, however, uses variable speed technology. It can precisely adjust its running speed and therefore its cooling output anywhere from a low level up to its maximum capacity to continuously match the actual cooling demand of the space at any given moment.
So it's more like a dimmer switch than an on-off switch.
That's a great analogy. Instead of constantly stopping and starting at full power, it ramps up or down smoothly. This leads to several key benefits. Much greater energy efficiency, especially at partial load conditions, which is most of the time. Much quieter operation because it's not constantly slamming on and off. Less wear and tear on the compressor, and more stable, consistent indoor temperatures without those noticeable swings you get with cycling units.
So seeing inverter on the box is generally a good sign for efficiency and comfort.
Generally, yes. It's a significant technological step up from basic fixed-speed units.
Okay, let's apply this TR-based sizing to a commercial setting. The source gives a sample project, a commercial bank, with a floor area of 110 square meters. It assumes an area per TR of 20 SQM for a bank, which falls right within that 20 to 25 SQM TR range we just saw in Table 3. How do we calculate the aircon requirement here, and what are the practical implications of the different options from the catalog?
Okay, so for step 1, solving for the cooling capacity of the room. Our assumption for a commercial bank as given is 20 SQM per TR. The total area of the bank is 110 SQM, so the aircon requirement equals total area divided by the area per TR assumption. That's 110 SQM, 20 SQM per TR equals 5.5 TR.
Okay, so this bank needs a total cooling capacity of 5.5 tons of refrigeration.
That's our target based on this preliminary calculation. Now, we need to look at Table 4, the capacity of split-type aircon, Koppel Super Inverter 3 series, to find units or combinations of units that add up to roughly 5.5 TR. The source presents 2 possible recommendations based on the models in that table. Option 1, use 4 units of the KV18WM AR-F21C model. Looking at the table, each of these units is rated at 1.60 TR. So 4 units would give a total capacity of 6.4 TR, 4 times 1.60 TR.
That's quite a bit higher than the 5.5 TR target, about 16% over.
It is. It would provide ample cooling, likely ensuring quick cool-down times and handling peak loads comfortably. Oversizing slightly is often done as a safety factor in commercial settings. Option 2 presented is use 2 units of the KD24WN AR-F21C model. Each of these units, according to the table, is rated at 2.0 TR. So 2 units would provide a total capacity of 4.0 TR, 2 times 2.0 TR.
Wait, 4.0 TR, but we calculated a need for 5.5 TR. That seems significantly undersized.
It does seem undersized, based purely on the initial 20S MTR assumption. This highlights a key point. These shorthand calculations and table lookups are for preliminary design. Perhaps the 20S QMTR was conservative, or maybe the designer knows specific details about this bank. Excellent insulation, low solar gain, lower than average occupancy that justify a lower capacity. Or maybe the source is simply showing examples of how to use the table. And in a real design, you might need to combine different unit sizes, for example, one 2.0 TR and two 1.6 TR units, or use a different model entirely to get closer to the target 5.5 TR.
Okay, so the recommendations are more illustrative of the process than definitive solutions for this specific bank.
Exactly. The key is calculating the target load, 5.5 TR here, and then using the catalog to select a combination of units that best meets that target, considering efficiency, EER, unit type, wall, cassette, etc., and other factors.
For a commercial bank, though, the choice between using multiple smaller units, like 4 1.6 TR units to get 6.4 TR, versus fewer larger units, maybe trying to find 2 units that total closer to 5.5 TR, is a significant one. It impacts not just the initial cost, but also long-term operation. How does this choice impact energy bills, future scalability, and overall functionality for a critical environment like a bank? This raises an important question for facility managers, doesn't it?
It absolutely does. For a commercial facility like a bank, the decision between using multiple smaller units versus fewer larger units has profound implications, going well beyond just hitting the target TR number. Firstly, consider zoning and flexibility. A bank isn't just one big room. It often has distinct areas: the main lobby, teller stations, private offices, maybe a vault area, and critically, often a small server room or IT closet.
Right, all with different cooling needs.
Precisely. Using multiple smaller units, like the four 1.6 TR units, allows for much greater zoning and localized control. You can cool only the occupied areas, or adjust temperatures precisely for different functions, maybe keep the server room colder than the lobby. This optimizes comfort and, crucially, energy use. Fewer, larger units offer less granular control. Secondly, and perhaps most importantly for a bank, is redundancy and reliability. Downtime due to equipment failure is extremely costly for a financial institution. If one of the four smaller units goes down, the bank still has 75% of its design cooling capacity operational, which might be enough to keep critical areas functional until repairs are made.
But if one of only two larger units fails,
You've lost 50% of your cooling capacity instantly. This could lead to rapid overheating, especially in sensitive areas like the server room, potentially disrupting operations. Multiple units offer critical redundancy, significantly enhancing business continuity.
that's a huge factor for a business.
Definitely. Thirdly, think about energy efficiency at partial load. Even with inverter technology, multiple smaller units working together can often operate more efficiently under partial load conditions, which is most of the time, than one or two very large units. Each small unit can modulate down to a very low level, precisely matching the reduced heat load in its zone. A single larger unit, even an inverter, might still be oversized for average conditions and could end up cycling more or operating less efficiently at its minimum capacity. Fourthly, aesthetics and air distribution. We talked about the different FCU types. Using multiple indoor units, maybe ceiling cassettes in the lobby and wall mounts in offices, offers better aesthetic integration into a commercial space compared to trying to cool everything with one or two massive, potentially obtrusive units. Strategically placed multiple units can also achieve superior air distribution, preventing uncomfortable drafts or stagnant hot-cold spots, which is crucial for both customer and employee comfort. And finally, scalability. If the bank layout changes, or if its internal heat loads increase, for example, adding more computers or server racks in the future, it might be easier and cheaper to add or upgrade individual units within a multi-unit system, rather than having to replace one very large, potentially custom-designed centralized system.
So it sounds like for a commercial application like a bank, despite potentially higher upfront costs for buying and installing more individual units, the long-term benefits in terms of efficiency, reliability, comfort, and flexibility often make using multiple smaller split systems the more sensible and strategic choice.
In many cases, yes. That modularity and redundancy are highly valuable in commercial settings. And remember, step 2, just like with the unitary system, involves specifying the precise location of both the outdoor aircon condensing units, ACCUs, and the indoor fan coil units, FCUs, along with necessary dimensions, mounting details, and condensate drainage routes. For a commercial bank, the ACCUs would likely be grouped together on the rooftop or in a dedicated service yard outside, carefully placed to minimize noise impact and ensure adequate airflow for heat rejection away from pedestrian areas. The indoor FCUs would be selected and located based on the interior design and functional needs of each space, perhaps ceiling cassettes integrated into the lobby ceiling grid and wall-mounted units in the private offices.
So the planning involves considering both the inside and outside components carefully.
Absolutely. Careful planning here ensures not only functional cooling, but also seamless aesthetic integration, compliance with building codes like noise ordinances or visual impact rules, and importantly, ease of future access for maintenance. This level of detailed planning is what separates a truly well-designed, effective HVAC system from just a basic installation.
We've really covered a lot of ground today. It feels like we've gone from the macro climate down to the micro details of system selection. We started with the incredibly challenging hot-humid climate of Cebu and its direct impact on human comfort, diving deep into that temperature and humidity data that shows just how far outside our natural comfort zone these conditions are, pretty much year-round. Then we moved into the fundamental principles of bioclimatic analysis, understanding how smart designers leverage climate data first to inform intelligent, passive design strategies before even thinking about machines. We clarified what air conditioning truly means according to the engineers, far more than just cooling. It's about simultaneously managing temperature, humidity, cleanliness, and distribution. And then we explored the two most common workhorses, the unitary window wall type and the flexible split type systems. We looked at their pros and cons, walked through practical sizing examples using those shorthand rules and catalog tables from a small office to a commercial bank, and even discussed the nuances of choosing between one large unit or multiple smaller ones. So, what does this all mean for you, our curious listener? If you're living in a hot, humid place or designing for one, what are the key takeaways from this deep dive?
I think there are a few crucial points to really internalize. The first critical takeaway is the absolute undeniable importance of understanding your specific local climate data temperature and, crucially, relative humidity, and comparing it rigorously to human comfort limits before you make any design decisions or purchase any equipment. This data-driven approach is foundational. It tells you exactly what problem you're trying to solve.
So don't just guess based on how it feels.
Exactly. Second, we saw the vital role of bioclimatic analysis in informing passive design strategies first. Think about how the building itself, its orientation, shading, ventilation materials, can naturally mitigate heat and humidity. Optimize the building before relying solely on active mechanical systems like AC. Every bit of cooling the building does passively is energy saved. Third, remember the nuanced definition of air conditioning. It goes far beyond simple cooling. It's about holistic air treatment, simultaneously controlling temperature, humidity, cleanliness, air filtration, and distribution for a truly healthy and comfortable indoor environment. Don't forget the humidity and air quality aspect.
Right, it's a package deal.
It is. Fourth, understanding the practical differences between unitary, window wall, and split-type systems is crucial for making informed choices. We've reiterated their respective advantages and disadvantages: cost, noise, aesthetics, flexibility, maintenance. The best choice depends on your specific situation: budget, space constraints, how much you value quietness or aesthetics, and long-term considerations. And finally, the value of those shorthand computations for preliminary design and understanding AC capacities cannot be overstated. While not a substitute for detailed engineering, they provide quick, actionable estimates to get a project started on the right foot, helping you select a system that is appropriately sized, not grossly oversized or undersized, for the unique demands of your space and climate.
And why does all this matter?
Ultimately, it all matters because it's about ensuring a good quality indoor environment. It's about creating spaces where people can be comfortable, healthy, and productive. This requires thoughtful design solutions that truly respond to those specific climatic conditions we talked about. It's the difference between merely surviving the heat and humidity and actually thriving in a well-designed, comfortable indoor environment.
If we connect this to the bigger picture, this deep dive into air conditioning and hot, humid climates really shows us that comfort isn't just about escaping the heat. It's a finely tuned balance of temperature, humidity, air quality, maybe even air movement, meticulously engineered to make our indoor lives not just tolerable, but truly comfortable. It's a fascinating testament to how human ingenuity addresses specific environmental challenges. But as we look to the future, in a world where climates are clearly shifting, becoming hotter in many places, and energy demands are consistently growing, it raises some big questions, doesn't it? How might continued innovation in both bioclimatic design, getting smarter about passive strategies, and in air conditioning systems themselves pave the way for more sustainable comfort? How can we minimize our environmental footprint from cooling, which is substantial, while maximizing human well-being, especially as more of the global population experiences these hotter, more humid conditions? And what other factors, perhaps the increasing importance of verified indoor air quality in a post-pandemic world, or even the psychological comfort derived from things like daylighting or a connection to nature, might become even more crucial in our future definitions of indoor comfort? Are we pushing the boundaries of what we expect and need from our conditioned spaces? Lots to think about there. Thank you for joining us on this deep dive. Keep learning, keep questioning, and keep exploring the fascinating world around us.